Hello and welcome back. In this video I'd like to talk about three sort of special kinds of motion. One is straight line motion, so if our object is moving along a line. Another is circular motion, which we saw an example of in the last video. And then circular motion is actually a special case of another kind of motion, and that is motion with a constant length of position. So we're always the same distance from some starting point. So we'll start here with straight line motion. I just want to consider what is my velocity if I'm moving along a straight line, what's my acceleration, and what's my speed. So we know straight line motion, the vector valued function for a line is given by this, right? With x naught, y naught, z naught being just some point on the line, and then a, b, c being my direction vector. So let's remember that. My direction is a, b, c. And this also might have a length to it, right? It's not a unit vector necessarily. And then we know that x naught, y naught, z naught is some fixed point, let's call it p naught, on the line. Just some fixed point. Something that we already know is on the line. So let's say we do derivative of position. So r prime of t, we know this is the same as velocity. This is how we recover velocity. And this gives us, so here in this coordinate, we'll just get a. In this coordinate, we'll get b. And in this coordinate, we'll get c. And so this should make sense to us that it points in the direction of motion, because my direction vector for the line is the exact same as my velocity vector. All right, so that's an important thing to note. What's my speed? Remember, this is a scalar valued function. Speed is magnitude of velocity, so this is going to be square root of a squared plus b squared plus c squared. And that is constant, right? Dependent on my direction vector. This is a constant velocity. We can move along a straight line and not have constant velocity, so it's possible I change my input variable here and we accelerate along the line. But if our straight line motion is just given by this, then our speed is constant and our direction is constant. And so what should be our acceleration? Well, we can either just think through it. It should be the zero vector because we're not changing speed or direction. Or we could take the derivative of velocity, or we could take the second derivative of position. In either case, we'll end up with the zero vector, 0, 0, 0, right? No t's in here, so we just get zeros. So for straight line motion given by this equation, our standard form for a straight line, we get zero acceleration, constant velocity, constant speed. So that's sort of maybe the simplest case of motion in 3 dimensions. A little bit more complicated, but also a sort of special case is circular motion. Again, I want to find velocity. And remember, we did an example in the last video where a was 3. So derivative of this, I'll get minus a sine of t. Here I'll get a cosine of t. And this is just in 2 dimensions, right? It's circular motion in 2 dimensions. And so that's my velocity. We can look at speed. That's the magnitude of my velocity function. It's a scalar. I get square root of minus a sine t squared. So that's a squared sine squared of t plus a squared cosine squared t. We know sine squared plus cosine squared is 1. So this is just square root of a squared, which is just a, because we know a is, well, we'll assume a is positive. I'm going to say that here, a positive. Right, so there's velocity and speed. Speed is constant, right? It's just this constant variable a, or constant a. But the direction is changing, right? The direction of velocity is changing. Or rather, the direction of motion is changing. So my a of t should be not the zero vector. It's the first derivative of velocity or second derivative of position. So I'll take a derivative of this guy. That gives me minus a cosine t, and then a minus a sine t. And so when we did that specific example with a equal to 3, we're getting a lot of the same things coming out of that. In particular, we have constant speed along the circle, and we have that my acceleration is the negative of my position, right? This is negative r of t. So we're recovering all those same things, but now in general, right? My speed is this constant a. It was 3 in the previous example, but here it's a in general. So this is a lot more general than that one example. So this is important. One thing to note here is that my position is orthogonal to my velocity. So I'd like to show you why that's happening with this general, in this general setting. So if I do r of t, remember how we test for orthogonality. We take the dot product. If that turns out to be 0, we know that the vectors are orthogonal. So I'm going to take r of t and dot it with v of t. And let's see what we get. So r of t here, so I'll do a cosine t times minus a sine t. So that's going to be what? Minus a squared cosine t sine t. And then the y components, a sine t times a cosine t. So this is going to be plus a squared cosine t sine t. And those completely balance each other out. We get 0. So what that tells us is that r and v are orthogonal. So the angle between them is 90 degrees or pi over 2 radians. This also means, since acceleration is parallel to position, right, this tells us acceleration parallel to position. It's the opposite direction, but remember, parallel just means a constant or a scalar multiple of one another. So acceleration is parallel to position. So if r and v are orthogonal and a is parallel to r, then a and v are orthogonal. So that is also true for circular motion like this. So this is circular motion in 2 dimensions, and we can recover all these great facts. But there's other ways to generalize this beyond just circular motion. For instance, a lot of this stuff is also going to be true if we're traveling on some curve on a sphere rather than on a circle, right? A circle is just, we can think of it like a cross-section of a sphere. In 3 dimensions, we can think of motion on a sphere and see if some of these observations hold there as well. So that's this more general type of motion, motion with constant magnitude of r. So the distance between the object and the origin is constant. So I'd like to show you that in general, if we have constant r, so if we're moving on a circle or on a sphere centered at the origin, then my position and velocity are going to be equal to 0. So this is a really fun thing to prove. All we need to know is that the magnitude of r is constant. So I'm going to say let magnitude of r just be some constant c. That's our assumption. What that tells me then is magnitude of r, just bear with me, magnitude of r squared will be c squared. And remember that the magnitude of a vector squared is the same as the vector dot product with itself. So what this tells me is that r dot r is equal to c squared. All right. So you might wonder why I just did that, why I wanted to find that r dot r is c squared. Well, this is going to be really cool. Let's see. So I want to prove that r dot v is equal to 0. I know v is the first derivative of r. So what I'm going to do is I'm going to differentiate both sides of this equation with respect to t, right? R is dependent on t, but this constant c is not. So its derivative with respect to t is 0. So I'm going to take a derivative of both sides, r dot r, equal to derivative with respect to t of c squared. Again, r is changing with time in general. C is a constant, so it's not. So this turns out to be 0. And what do I get over here? Well, I can do the dot product rule for derivatives. So this is derivative of the first, r prime, dot the second, dot r, plus the first, dot the derivative of the second. So, and remember, dot product is commutative, so this is really 2. We can think of it as r prime dot r. And that is equal to 0. So what that tells me then is r prime dot r is equal to 0, and r prime is velocity. So this tells me velocity dot position is equal to 0. Ha ha! That's exactly what we wanted to show, right? This means that v and r are orthogonal. So this is going to happen. It's more general than the circular motion. This is going to happen. This phenomenon, r and v being orthogonal to each other at all points on the curve, happens when the magnitude of my position vector is constant. So that is on circular motion, or if my motion is on a sphere centered at the origin. It'll also happen then. So this is a pretty nice result that comes from that. Okay, that is it for this video. Please join me next time.